Greetings everyone, it's time for SpongeBob, and I mean really, it's time for motion in two dimension. I'm going to go ahead and check out this first problem and show you how we're going to deal with a projectile that's launched horizontally, not at an angle, off of a cliff. So what I have here, and the first thing I'm going to do is I'm going to change g to -10 because I like down to be negative, and that's something I just want to get in the habit of doing so that we're all talking the same language. Okay, so what we have to do in this problem is a projectile is something that has horizontal and vertical motion occurring simultaneously and independently. So we're going to ignore drag in all of these problems. And the first one says we have a cannonball launched horizontally from a cliff 80 meters above the ground. So the first thing I'm going to do is I'm going to start setting up a coordinate system so that I can see what's going on here. Now this 120 meters is talking about horizontally there's 120. So I'm going to go back through and try to find a way to set up my coordinate system. I'm going to make 0 be the beginning, and I can divide this up into every 2 is going to be 30. So 60, 90, 120. I'm going to do the same thing with my 80. I'm going to start up there with 80, and then we're going to go 60, 40, 20, and then that's going to be our vertical 0 position. Okay, the next thing I would recommend doing is to set up kind of a little grid line where your coordinate axes is kind of like this box. And you'll see why I'm doing this in a second. We're going to add to this idea of this vertical box. But what I want to do is I want to pretend for a moment that our projectile is actually doing two separate things. It's being launched horizontally and it's falling vertically. So if we can put the two together, we're going to see that our projectile's path is going to be really easy to find. So the first thing I want to do is I want to think back to the free fall practice and just pretend for a moment that that cannonball has just dropped. It just rolled out of the cannon and didn't even launch horizontally. It just freely fell. So I'm going to use this table to the right hand side and talk about, okay, what's going to happen if this thing were just to freely fall. So I'm going to start filling this in. 1, 2, 3, 4. And so it starts at a 0 position. It starts not moving. Now acceleration due to gravity is -10, so I'm going to just, every second it's going to be moving 10 meters per second faster in that negative direction. So it's speeding up as it falls towards the ground. And then we can find our delta y, our little change in y, by using that first equation. Our delta y is equal to 1/2 g delta t squared plus vi y delta t. So if I'm judging everything from when the cannonball dropped, I can just assume that my initial velocity is 0, make my life easier, and I don't have to worry about that second term. Now as I go through and plug in my different times for my delta t squared, we're going to be able to populate this table. After 1 second, the object is going to fall in 5 meters, excuse me, this is 80 meters. So after 1 second, my little delta y is going to be equal to 5 meters, negative 5 meters. So I was at 80, well now I'm at 75. After 2 seconds, my delta y is going to be -20 meters, which means my new position is 20 meters away from where I started. So 2 seconds ago I was at 80, now I'm at 60. After 3 seconds, I plug in a 3 for my delta t. After 3 seconds, we're looking at a fall, a -45 meters is my delta y. So it's going to be 45 away from where it was. Now we're at 35. And then the last fall, after 4 seconds, I've fallen exactly 80 meters. That's going to be where I hit the ground. So we're going to go ahead and put 80 meters down there. That's my 35. Okay, so this is really familiar with us. This is what's going to happen to this object. So I'm going to go ahead and go over to the left-hand side, and I'm going to just sketch in where the ball was at those moments in time. So at 0 seconds, it was at 80, so I'm going to leave it there. At 1 second, it was at 75. So I'm going to guesstimate where 75 is on here. I'm just going to draw a little circle here. I'm not going to fill this in. Okay, I'm going to do the same thing at 60 meters. It's fallen for a couple seconds, so I'm going to go ahead and draw what looks like 60 to me. I'm going to draw the third second, which is going to be at 35 meters, so I'm going to guesstimate where that's going to be, roughly down here. And then lastly, it's going to be at the ground. So what you can do with this is showing you where the object would be roughly if it were to just fall. And you probably would want to do this over on the right hand side also, closer to where you can actually see. So we have our 75 here, 75, we have our 60, oops, excuse me, we have our 35, which is going to be somewhere down around here, and then we have our at the bottom. So what this is showing is where the object would be if it just fell. Okay, vertical motion is taken care of. Thankfully, it behaves independently of horizontal motion. In other words, it doesn't matter what the object's doing horizontally, it will fall that much space in that amount of time, regardless of how fast I launch it horizontally. So horizontally, I'm going to go ahead and look at my situation, and it says the can leaves at 30 meters per second. So when I launch this thing out, my initial velocity x is, I'll just break this into two little pieces here. Here's my x, here's my y. My initial velocity x, or Vix, is equal to 30 meters per second. So that means that every second my cannon is traveled 30 meters. So I'm going to go ahead and draw after 30 meters. We're sitting here. After another second, we're sitting at 60. After another second, we're sitting at 90. After another second, we're sitting at 120. And so on. So this is constant velocity motion. This is where our ball would be if gravity all of a sudden stopped working. It would just keep shooting out into infinity until another force would act upon it. So what we're going to do now is we're going to take this and we're going to draw down some dotted lines from horizontally where the projectile would be. And then we're going to draw some lines vertically for where vertically the projectile has fallen in that amount of time, regardless of if it's moving or not. And what we can do now is we can say, all right, after 1 second, the ball has moved to here horizontally and to here vertically. It's fallen and it's moved horizontally. So I'm going to draw in here. That's where the object is. After 2 seconds, my object has moved horizontally over to the 60 meter mark. And vertically, it's fallen down to the 60 meter mark. So I'm going to draw my line here. After 3 seconds, we're going to draw our line, and after 4 seconds, it hit the ground. So now that I have my positions, I can go ahead and draw my velocity arrows. So initially, when it first came out of the barrel, it hadn't fallen at all yet. It had 0 vertical velocity, but it did have horizontal acceleration. So I'm going to draw a horizontal vector. And that horizontal velocity vector is going to stay the same size. That was 30 meters per second. So I'm going to go ahead and draw those all in here. But what I need to update now is as it fell, it started picking up velocity vertically. So at the beginning there was no velocity vertically, but it was accelerating downward. So I'm going to draw a little acceleration vector, half arrow there, pointing down. And I'm going to go over here and I'm going to start drawing, okay, it moved -10. Third that side. So here's -10 meters per second. And then it was -20 meters per second. And then it was -30 meters per second. Still accelerating down. And then down here at the bottom, now we're -40 meters per second. And it's still accelerating down, so I'm going to just draw acceleration vectors all throughout. And the acceleration vector is representing my -10 meters per second squared of vertical acceleration. So now I've drawn my motion map. The next thing we need to do is these are what are called velocity vectors that are components. So there's our Vx component. I'll just use this big one down here. Here's our Vx component. And then here is our Vy component. That just means the velocity is acting purely horizontally and purely vertically. But what happens is the actual ball at that instant in time isn't moving just horizontally or isn't moving just vertically. It's moving a combination of the two. It's flying through space at the component. When we add those components together, what is called the resultant velocity. It's the resultant. It's kind of the opposite of what we did with forces, where we broke apart a resultant vector and broke it into components. Now we're going to take the components and we're going to go ahead and draw what's called the resultant vector. That's actually what the object's doing at that instant in time. So we're going to call this VR, and that stands for resultant. So going back through here, we can draw, and we need to draw, the resultant vectors for all of these. And we can just do this by drawing a parallelogram around those vectors. And there was nothing. And we'll do the same thing down here. And so that's showing where the what the resultant vector is at that instant in time. And if we knew the angle of a little bit more about this, we're going to actually be able to solve for that resultant vector based upon the values of these other ones. Alright, so this is a lot of information. So what I want to do is I want to take this and I want to do some mathematical work with it. So the first part says A, how long does it take for the ball to reach the ground? So the delta y to reach the ground was an overall of it reached the ground, it took 4 seconds. And just looking at this data table, I can prove that to you. But I want to go ahead and solve for another way in case you didn't want to make that data table. What I would do is in my knowns list, where I break apart what's happening vertically and what's happening horizontally, I would start writing in some information. The really cool thing is that the delta t for both of these is going to be what is shared for both vertical and horizontal. What they have in common is how long they're in the air, because as soon as it hits something, it stops moving, then the projectile launches over. So what they have in common is they both have the same delta t, and in this case we don't know what that is. Okay, that was our question mark. But there's some other information. Delta y was equal to 80 meters. Our g was negative 10 meters per second squared. Our initial velocity vertically, thankfully, was only 0 meters per second. And then we already looked at our horizontal velocity. So what these two share in common is that whatever time this thing hits the ground, that's going to be true of both of these. Okay, so that was our delta t was equal to question mark. It would show up on both of these. Okay, so with all those knowns, we can use our equation. Delta y is equal to 1/2 g delta t squared plus v I y delta t. Because the initial velocity is 0, that term is going to cancel out. And I'm going to rearrange for delta t. When I do so, delta t is equal to the square root of 2 delta y over g. And then when I plug, okay, I'm just going through Keepa here, 2 times 80 meters divided by negative 10 meters per second squared. I'm going to be really careful about the signs because my final position was 0 and my initial position was 80. 0 minus 80 makes this a negative 80. So 2 times negative 80 divided by negative 10, take the square root of that, and we're going to get negatives cancel our 4 seconds. So at 4 seconds is when it hits the ground. This data table here, which is another way you can solve the problem, confirms that it's 4 seconds. It confirms our delta t. The last part says, what is the horizontal range of the ball? Show your work. Because the ball is in the air for 4 seconds in both cases, then that means that I can take and use my horizontal motion. So if I go back and look at my first back to constant velocity, our change in position is equal to the average velocity times my change in time. So I'm going to go ahead and use this equation that's listed at the top, and we're going to plug in, well, our average velocity was 30 meters per second, times our delta t was 4 seconds, seconds cancel, and we're left with 120 meters. That's how far we made it, because the delta t was the same. We've already done part C. We've made a qualitative motion map, and we've also shown the resultant vector. The table helped us out. Okay, part D, E, F, and G says, what is the horizontal speed when it hits the ground? When it hits the ground, because nothing has interfered with its horizontal motion, nothing has caused it to slow down or speed up, there has been no external forces horizontally, it's going to keep doing what it was doing. So it's going to keep that 30 meters per second that it had when it launched out of the cannon horizontally, because nothing messed with it horizontally. It just kept moving. There was no friction, there was no drag, so it kept that same 30 meters per second. Part E says, what is the vertical speed when it hits the ground? Show your work. Vertically, when it hit the ground, looking at the table, we said it was negative 40, just based upon what happens with velocity. But if you wanted to do it in a one point and do it a little bit differently, we could use our equation that the final velocity y is equal to g delta t plus initial velocity y. And this is coming from our equation, so when that term goes away because there's no initial velocity, it started from rest, we're going to go ahead and get that negative 10 meters per second squared Vfy is equal to negative 10 meters per second squared, and that's going to all be times my delta t, which was 4 seconds when it hit the ground, and so we get our negative 40 meters per second squared. Meters per second. And the question does ask for speed, so it's really just the 40. Okay, speed is a scalar, it doesn't have a direction. The last part, part F, what is the resultant speed of the ball when it hits? Show your work. This is where we have to take the resultant vector and solve for it. It's going to be pretty simple though once we use some trig. So what I need to do, I like to draw and kind of blow this up a little bit. What's happening at that moment here? I'm going to draw a circle around this now. Okay, so what's happening right here? So when I come down, this is when it hits the ground. I'm going to blow this up for you and recap what was going on. There were 30 meters per second of horizontal velocity, and at that instant we had our 40 meters per second going downwards. Now this was negative, but I'm just going to leave it as 40 right now because when I'm dealing with these triangles, I'm okay with just getting the magnitude. So I'm going to go ahead and draw this parallelogram around it. We're going to draw our resultant vector going down to that corner. And it says, what is going to be the hypotenuse of this? So all this takes is some simple trig. I have two sides. This resultant vector is the hypotenuse. So if I go back to Pythagorean theorem, a squared plus b squared equals c squared. Rearrange for this, solve for c. C ends up being equal to the square root of a squared plus b squared. And so c is equal to the square root of a, is just one of those sides, 40 meters per second squared, plus b squared, which is 30 meters per second squared. And when I take all of that, I'm going to get this, and I take the square root of it, I'm going to get that c was 50 meters per second. That's my hypotenuse. Okay, that's what the ball actually was, because not only was it moving horizontally, but as soon as I started picking up enough vertical speed, we're going to go ahead and combine those, and we get 50 as the result, and that's actually how fast the ball is moving. The last question says, what angle relative to the ground does it hit? Well, if I look at this thing here, I remember that the ground is actually right along my horizontal. So relative to the ground means from the ground I'm going to draw an angle, and we'll call that little angle theta. So we're going to use some arc sine in order to do this. So my vertical, the opposite of this angle was our 40 meters per second. The adjacent to this angle is 30. The sine dealing with opposites and adjacent is tangent. And I need to use the arc tangent to find the angle. So tan minus 1 of my opposite over my adjacent is going to be equal to theta. So all I need to do is take tangent minus 1. The opposite side was 40. The adjacent side was 30. Those units cancel. And when I do that, I'm going to get my angle as 53.1 degrees. Okay, so this is how we deal with problems, projectiles that are launched horizontally, and I hope that this was helpful.